Okay, so welcome to everybody to the last session of this analysis and PDE conference. So I will pass the chair to Professor Juan Limaco, who will be in charge of the session of Professor Enrique Suazua. Thank you.
Enrique. Enrique, good morning.
Good morning, Juan.
We can start.
Yes, but so we are 1 minute early, I think, but if you wish.
Maybe I suggest to wait 1 minute, maybe to start exactly at 2 p.m. in Central European time.
1 minute. Okay, is okay. It's an honor for me to introduce to Professor Enrique Suazua, who is one of the strongest mathematicians in the area of control theory and partial differential equation today. Professor Suazua received his doctorate in 1988 in France under the guidance of Alain Aroux, and currently he has already oriented 30 PhD students and has 65 descendants. Likewise, his scientific production is high, having published 517 articles and has approximately 18,691 citations. He is Chief Professor in Applied Analysis at the University of Erlangen-Nuremberg, Germany, and also from the Autonomous University of Madrid, and winner of the Alexander von Humboldt Professorship. On this occasion, Professor Suazua will give the plenary entitled Dissipation Decay on Hypocursivity for Hyperbolic System. Welcome, Dr. Suazua, and you can start.
Thank you, Juan. Thank you for the organizers of this great event. Thank you also to, in particular, Duvan Cardona, that I had the pleasure to meet personally 2 years ago or so while he was visiting our group in Bilbao, and since then I had the honor of keeping a constant cooperation with him. I'm particularly glad that we are doing this in this context of Latin American cooperation. Actually, yesterday we were running from here in Erlangen a short meeting with a number of colleagues in Latin America to reinforce the collaboration we are already developing with the BILAT, the Center for Cooperation between Bayern, Baviera, the Länder, the state of Germany in which our university is in Erlangen. The BILAT aims to develop continuous academic and scientific cooperation with all countries, all institutions in Latin America, And yesterday we were running this meeting to inform about the opportunities we have here. And yeah, of course, for those that didn't attend, and for those that are interested on pursuing this, exploring these possible cooperations, you can directly get in contact with me, and I will put you in contact with the people in charge in BILAT. So today we are here to talk about math, and in particular, a topic that I find extremely interesting in PDE analysis, that, as you will see, connects several areas, sometimes in an unexpected manner. Basically, my presentation will be inspired in three articles. The one first with Karine Bochard, that was published in 2011. So that was, the paper was conceived by basically 15 years back when Karine was visiting us in Madrid as a postdoc. And then more recently, I have revisited this topic in collaboration with Timothy Simbarang, who is a postdoc in our team. He has been in our team last year and also this year. And also Nicola Diniti, that was a PhD student in our group. Now he is a postdoc in EPFL Lausanne. And Dr. So, who an expert in this area of hyperbolic PDEs, was visiting us for a few months from China recently. So, as I said, this is a topic in which unexpected links emerge. Although, as it happens usually, once you observe, you understand why these links arise, you find them quite natural. But in principle, it was not completely expected. This is why I would like to start my lecture with a slide that probably many of you already have seen in my lectures. I like this one particularly because it's really at the heart of many of the potential developments in, say, an effective developments in control theory, but also with links with other areas, which somehow shows that the scale of PDE analysis reflects this magic unity of mathematics and the fact that different fields are often unexpectedly related through, different problems that eventually require of the same kind of tools and fundamental ideas. And this is one of them. So this is a classical topic, control theory, that was developed essentially during the Industrial Revolution. It has exploded after the Second World War, of course, with all the different technological and industrial applications, and also the possibility of, developing, high performant numerical simulations. And that by, the mid-50s, already had a number of fundamental concepts well identified. And this is one of them. So this was one of the contributions of Richard Kalman to the theory of control. There are, of course, many others that you know, like the Pontryagin maximum principle or the principle of dynamic programming by Bellman, leading to the Hamilton-Jacobi-Bellman equations, nowadays so relevant, for instance, in reinforcement learning, one of the branches of, say, machine learning and artificial intelligence. And so this is a key concept and a fundamental theorem that is very easy to understand. Actually, the only thing you need to know is a little bit of linear algebra and just, the basic concepts about linear differential equations. So this is how the model was formulated by Kalman. Already in this formulation, you already enjoy of the clarity that it brings, right? So it makes control problems to be defined in a very concrete and easy to handle manner. So the linear system is described by the differential equation x prime of t equal ax plus bu, right? So A is the matrix driving the dynamics. in the absence of control, if u were 0, u is the control. If u were 0, this will be x prime equal ax. And then this is a classical Cauchy problem generated by the matrix A. The solution will be simply the operator exponential at applied to the initial datum x0. And this leads to a unique solution, which is analytic in time, which depends analytically on the initial datum, and so on. Now, of course, this is linear dynamics. In many applications, models are nonlinear and has to use nonlinear techniques. In principle, in particular, the theorem of implicit functions or inverse functions to move from the linear to the nonlinear context. Also, very often, one needs to deal with partial differential equations, which means that the matrix A becomes necessarily an unbounded operator in an infinite dimensional Banach space or Hilbert space, which introduces substantial difficulties. This is why there is a significant research in PDE control is still ongoing, because the gap between finite and infinite dimensions is hard to fill, and it depends very much on the type of PDE you are considering, the nonlinearities, the regularity of the coefficients, and so on. Right? But in this particular context, you already can fit plenty of possible models of interest, in particular, for instance, telecommunication networks or social networks. So if you think in social networks, so here we are like, I don't know, 60 people in this lecture. We are a small social network of 60 people, right? So we can represent our opinion on a given topic, for instance, hyperbolic systems, our proximity to this topic. We can describe it through a vector x, right, with components x1, x60, in which in each component we are simply indicating how close we feel in the scale 0 to 1 to the topic of hyperbolic systems. And then, but this network, we are in interaction, we are all in constant, communication. The communication is not equally intensive for all of us. So the matrix A is the connectivity matrix that is really indicating how frequently, how intensively, the individual xi in the network is communicating with the individual xj in the same network, right? So A is the connectivity matrix. The information flows on this network through this, connectivity matrix, right? This makes that the information we have on this specific topic, hyperbolic system, is also transmitted through the network to the other individuals. And this is why our level of information, in principle, should be monotonic increasing, right? Raises, because even though, we are maybe not proactively seeking to learn something about this topic, well, there is, Duvan that organizes a lecture with Han and colleagues, and the lecture is about hyperbolic systems, then you attend, and then in this way you increase your know-how on this topic. So this connectivity matrix A is the one that really describes how the information is flowing in this network, something that is represented simply by this vector state x1 into x60. But then, in the context of control, we go a little bit beyond the classical solvability issues of Cauchy problems, right? So typically, when we are in the context of ordinary or partial differential equations and dealing with Cauchy problems, we look to questions like existence, uniqueness, maybe long-time behavior of solutions, numerical analysis of solutions, right? Effective numerical approximation, scientific computing, simulations. And then in control theory, we go one step further, as it is often required in the technological and industrial applications. And we try to understand how the action, the design, and the use and the action of a suitable control, U of t, can modify the dynamics of the system. And this is something that is extremely important nowadays, right? For instance, these days you see how, the dynamics of Twitter is being criticized. Now Twitter is called X, I think, this social network, because some agents think that the information that is being provided about the last war between Israel and Palestine is not neutral. Well, we all know how, easily influencers can affect, can modify the state of opinion on a social network, sometimes even by using fake news. So why not, right? So the goal is not to inform transparently the population, but rather to push populations to believe, to think, to have an opinion, to vote for a given candidate. Yes, so even fake news are unfortunately acceptable nowadays, or at least employed, right? So this is the role of the control U. And I insist, you can be dealing with a huge network, millions of individuals, and the controllers, the ones that really have a strong influence, are just a few. Those that have millions of followers, so that whenever they say something in the social networks, this spreads rapidly, right? But the spreading, of course, depends on what? Depends on two matrices, right? The A and the B. The A we have described. The A is the interconnectivity of the matrix of the system. So, of course, how information spreads depends on the matrix A that is linking all the nodes of the system. But, of course, how efficient this control, this action, this added input into the system UT is depends very much also on the matrix B. So the matrix B could be, for instance, the locations of the nodes in which the action is being introduced, right? So this will be like, for instance, when we were experiencing the COVID infection, right? So which are the points where vaccines are being distributed, right? So B somehow describes where the controls are located. A describes the free dynamics of the system, the spreading of information along the system. And the game in control theory is to try to understand whether for such a system, which is completely described by the matrix A for the dynamics and B for the control, whether the system is controllable or not. This means that from any initial configuration, you can drive the system to any final configuration by the use of a smart control U depending on T. And the condition, the if and only if condition for the system to be controllable was given by Kalman, is this Kalman rank condition, which is purely algebraic. You check, and if it happens that the rank of this iterated matrix B, AB up to AN minus 1B is full, is equal to N, the same as the dimension of the system, 60 in this case, maybe now 71, I see. Okay, 71 and equal to 71. If the rank of this matrix is 71, then it means the system is controllable. So we will be effectively be able to communicate with every individual of this network to convey our message. But if the rank is not N, but is less, is say N minus 1, it means that there will be one component of the system, one individual in this system to whom we will not be able to convince, either because the information doesn't get to him, or it gets too weakly so that it's not sufficiently relevant, the action of the control, to modify his own opinion. So this is a purely algebraic condition that, at least conceptually, is easy to understand. And the proof of that result is very simple. You just write the variation of constant formula for the solution X, in which you will see, of course, the integral of exponential A t minus S applied to BU. So you see exponential A times B in this variation of constant formula. When you expand the exponential of A on power series, you see the powers of A multiplying B, as in the rank condition. And then you wonder why in this rank condition you stop at the power n minus 1. Well, you stop at the power n minus 1 simply because A is a zero of its characteristic polynomial. It means that the nth power of A is a linear combination of all the previous powers. And therefore, after the power n minus 1 of A, you don't add anything to the rack, to the necessity of filling the space through smart actions of the control. So this is a summary of control theory. And when you see this, you say, well, yeah, I mean, that's nice. Doesn't seem so complicated. It's good to know, but this has nothing to do with hyperbolic systems. But actually it does. So in the previous discussion on control, the control was the so-called open loop control. So you are allowed to, design offline your control, U depending on T, and then implement it on the system. But in practical applications, right, we often need the control to be defined in a feedback manner, right? And this is actually what we do when we drive a car, right? So we cannot plan our actions before leaving home. We have to be reactive. We have to be, very focused on driving, because there are events that may happen, a dog crossing the street, a red light, heavy rain, and these needs of our immediate reaction. So to be able to drive safely and successfully, it means then the control has to be given in a feedback form. This means that the control U of T has to be linked to the state xt of the system in this linear setting through a linear matrix. And then you see, for instance, by considering the simplest example that now links the topic of control with hyperbolic system, by considering the simplest case in which A is skew symmetric, right? So if A were skew symmetric, as it happens for the harmonic oscillator, for a discretized Schrödinger equation or a wave equation, right? The system is conservative. So A being skew symmetric, the norm trajectories live on spheres, right? So the norm doesn't change. Of course, there is plenty of room, right, in the n-1 dimensional sphere of Rn for trajectories to develop complex patterns. But when A is skew symmetric, the norm of the trajectory doesn't change a long time, right? And then the typical way of formulating the control problem is to say, okay, so if there is no control, the trajectory will rotate forever over, the surface of the n-1 sphere determined by the initial datum. The initial energy determines the radius of the sphere in which the trajectory will evolve forever, right? But now, through a damping operator, we want to push the trajectory to go down to zero exponentially. So how do you design such a matrix where the one you see in Formula 2 minus B star is a very good one? Why? Because if you just do the classical computation of the energy dissipation, right? You multiply the state, the equation by X, right? Scalarly in the Euclidean space, and check how the norm evolves. You employ the fact that A being skew symmetric, AXX is equal to 0, and you get the energy identity below, meaning that half of the time derivative of the norm of X squared is equal to minus B star X squared, right? And then, of course, this is non-negative. You see why I have chosen, L to be minus B star, because in this way, I succeed on making B star X times X to be a, say, non-negative quantity that with the minus sign produces the dissipation. And then you wonder, well, but is this sufficient to guarantee the exponential decay of solutions? Well, because you are in the finite dimensional case, things are not that complicated. You can use a spectral analysis or Lassalle's invariance principle using the energy as Lyapunov functions. You can do it in several ways. And you will get to the conclusion again that the dissipation is effective and the system decays exponentially if and only if the Kalman-Rank condition is fulfilled. Why? Because in case the Kalman-Rank condition is not fulfilled, you see what happens? It happens that there is an eigenvector of A that is on the kernel of B star, and then this eigenvector is not dissipated. There is one component of the system that is not dissipated, that you have forgotten, and therefore the system does not fully decay. There will be components of the system whose norm will be preserved. This will mean that you will reduce the dynamics of the system from an n-1 dimensional sphere to a sphere of lower dimension, but the loop will continue on those directions in which the damping was not effective. So again, the Kalman run condition. Okay, fantastic. Then, people, the first, comment you can make is, oh, but if I am getting an exponential decay thanks to Kalman, if I'm getting the exponential decay rate for this system, then if I increase the amplitude of the damping term, I should do better. Well, and the answer is no. And this is actually a topic that was already analyzed back in '68 by Lord Maxwell, the one that developed electromagnetism, because they already observed during the Industrial Revolution that very often the stabilizing governor mechanisms were not necessarily functioning better when they were designed more carefully, right? And it was Lord Maxwell who realized that, in fact, this was related to the capricious behavior of the exponential decay rate of the damped harmonic oscillator. So you see in this slide, this is very elementary. Again, bachelor level analysis. You consider the harmonic oscillator mx double prime plus rx. So this is a spring with mass m and resistance capital R. And you say, let me damp, let me add some friction, right, through the term K. K positive is the friction parameter, so that this spring, dissipates energy, is damped, and then converges to zero exponentially. So how does the decay rate depend on the amplitude of this damping parameter K? And it turns out, when you compute the roots of the characteristic polynomial, of the second order characteristic polynomial of this second order ODE, you realize that the pattern is the one indicated in this graph. So our intuition is correct for a small amplitude damping. So when K is 0, of course, the decay rate is 0 because the harmonic oscillator is a conservative system. 0 decay rate. You start increasing K, K is positive, then the harmonic oscillator starts decaying. But then there is a threshold, which is given by, in this case, K equal to 2 times the square root of the multiple of M and R, in which you reach the maximum decay rate, and beyond this threshold, the decay rate deteriorates. So that was an important result, right? So Maxwell made it very clear, and he warned people to say, listen, be careful, because even when control mechanisms are efficient, if you overdo, if you push the system too hard, you might get weaker results than the one you were expecting. So there is always a critical threshold, and beyond this critical threshold, this is the phenomenon so-called overdamping. Overdamping meaning that beyond this critical threshold K, the damping you are doing, the input you are introducing into the system is an energy, right, that you are spending in a useless manner because the response of the system is weaker. This is like an overdose, right? This is like when you go to the doctor, you go to the pharmacy, then you buy the tablets, and the tablets tell you, well, take 2 per day, but don't take 10, because not only this will not improve your health, but actually it will have, counterindications. This is overdamping, is like a saturation threshold that we have to keep in mind when dealing with the asymptotic behavior of conservative systems under damping. The warning from Maxwell is very clear. Be careful, things don't behave according to your human intuition, right? And this is the plot. And this is why things in control theory are complicated, right? So this is a nice video I found a few days ago in Twitter about, optimal parking of a car, right? So you see that, if we all were able to do, the computation, implement this optimal control strategy that has been computed, right? Of course, analytically using the dynamical system model corresponding to the driving of the car, we will be able to, park in just one shot, something that very often, is far from being the case, right? So you see here that just you take perfect measures, then you make the critical choices on the respective lengths, the angles, the, time to stop and now switch, the gear, right, to adopt a different angle and then go back. And then in just one iteration, you are perfectly packed, right? And very close to the pedestrian path, not 1 meter away, as it happens also very often. So this is the complexity of control theory. Things are intrinsically complex. They don't necessarily obey according to our intuition. Optimal control strategies are complex. And of course, when you are facing high dimensional complex modern applications like the one I was mentioning on social network, when you are dealing with millions of parameters and in the context of data science and so on, you definitely need to use the most powerful computers and algorithms in order to compute the optimal control strategies, right? Because even when you know that the Kalman rank condition is fulfilled, right? The Kalman rank condition guarantees that you can, but it doesn't tell you how you have to do it, right? And then, this computation of the optimal control strategies is something that requires further analysis, like, for instance, this very elementary but beautiful computation by Maxwell indicating, be careful, don't go beyond a given threshold because things get worse, or this other computation of parking a car in which you see to which extent it can be tricky to maneuver the car in an optimal manner. Okay, now let's get to the topic. This is a classical topic, nonlinear hyperbolic conservation laws. It has been a topic of investigation for the last 50 years or so. There are, the pioneering works by, in particular, Dafermos and Maida, many other authors also working in this topic. The model being, well, not simply classical hyperbolic conservation laws, but actually balanced laws, because there is a reaction term on the right-hand side, right, as it happens very often in applications of hyperbolic systems, right? So the hyperbolic systems are dealing with transport, nonlinear transport, but also there might be added forces that are represented by the right-hand side Q of W. So here the state is W, right? W is a vector, right? It's a vector with n components, right? So, right, it can be the different, fluid velocity, density, temperature, and so on, the classical components of that physical state, right? If you are thinking on traffic, it could be, traffic along the different lines of the highway, or traffic of different, say, car sizes, or it can be, the transport of different, say, particles in our cardiovascular system, right? The different components of these particles, of these components are described by the different variables W, right? So W is a column vector. It propagates along, this quasi-linear hyperbolic equation determined by the fluxes capital F, right? But there is a reaction term that is either damping or feeding the system so that, this transport phenomena is enhanced by, this added external force that can be, for instance, like a gravity force acting on the system, right? Okay, now there is the t variable. Of course, W depends on time, but there is the space variable. In principle, X, it belongs to the space Rm. So there are m components of the system. And then people, at that time were looking to, okay, can we describe, at least, analyze the Cauchy problem? Of course, finding global solutions for these problems is something that is tricky, because even in the absence of this reaction term, as you know, hyperbolic systems may develop shocks. This is what happens, to, for instance, the Barger's equation already. And then what is already formulated in the book by Maida at that time was to say, listen, maybe it's too much to expect that we will be able to understand this, say, balanced law system fully, but let us at least consider initial data that are close to equilibrium, right? So if we compute an equilibrium configuration, and then we, if this equilibrium configuration is stable, then when we start solving the Cauchy problem with an initial datum that is close to this equilibrium, we should be able to build global solutions that exist globally in time and that, in fact, get close to the equilibrium asymptotically. So what are the simplest equilibria for this system? Well, the simplest equilibria for this system are the functions W, which are independent of T, of course, to be an equilibrium, so time independent, but also X independent. So just a vector of constants, right? So what are the vector of constants that are equilibria for this system? Well, it's just the zeros of the reaction term capital Q, right? Because if W doesn't depend on X and T, the time and the X derivatives on the system will vanish, and it's just the zeros of capital Q. So let's then take W star to be a vector in which, the reaction term capital Q vanishes, and let us analyze the behavior of the system around this steady state. How do you do that? Well, you linearize the system, and when you linearize the system, you find a linear system of hyperbolic equations, right? Where, the linearization of the fluxes F leads to the matrices A, and the linearization of the matrix Q leads to the matrix B, right? Now, this is a linear system, constant coefficients, n hyperbolic equations, so it's a system of n hyperbolic equations coupled together through the matrices A and damped through the vector B. Of course, in practical applications, it happens that this vector B of this matrix B of damping, the damping is only effective in some of the components of the system. And this is what we represent, to simplify the presentation, by this block structure in which the B is 0 up to the last block D, which is the effective damping block. Well, now you have a linear system, partially damped, and of course you are interested in understanding the decay rate of solutions, because as I said, if you know the decay, then you can expect to prove that there is a stability of this steady state and that the nonlinear system will evolve towards this steady state globally in time out of initial data that are small perturbations of this steady state. And this is where you find the link with the previous control theory, because you say, how do I analyze the behavior of this partially dissipative hyperbolic system? Well, you think on it, you will immediately realize, well, it's not that easy. There are matrices A, matrix B, everything is mixed up, different directions of propagation on the hyperbolic system, different components damped differently by the matrix B. These components interacting through the coupling of the matrix A. This is really a mess. So how do you understand that? Well, you do it through the Fourier transform. You take the Fourier transform in a space, and then, of course, out of the matrices capital AI, it emerges the matrix A depending on the Fourier variable Xi, which is just the combination of the matrices AJ with the components Xj of the dual Fourier variable Xi, right? And you see, of course, there is an I in front of the A matrix because we are taking the Fourier transform of the first derivative in X, right? So if we assume that the matrices AJ are symmetric, this A matrix, depending on Xi, will be symmetric as well. But together with the I, the complex imaginary number, this becomes a skew-symmetric matrix. And B is a damping operator. And then you realize, oh, but this is exactly the setting in which I was before, right? It was a linear system, a skew-symmetric, in which the energy was preserved, on which a partial damping is acting. And we have seen that the condition for decay of that system was the Kalman run condition. And this is precisely what we aim. So we say, listen, if we are able now to guarantee that the B together with the A is fulfilling the Kalman run condition, then the solutions of this system will decay. Yes, but there is a but here, right? There is an important but. Because A depends on Xi. Xi is the dual Fourier parameter. So somehow when the dual Fourier parameter Xi is rotating in a Ren, the matrix A is also rotating with the Xi. And you are filling a whole manifold of matrices A depending on Xi, for which the Kalman run condition with respect to B has to be fulfilled. Even if this is the case, of course, the decay rate of this system will change and will depend on Xi. And we will get, decay rates as the one represented in the last line, exponential minus lambda depending on Xi. Well, this is something that was done back in the 85 by Shishuta Kawashima using energy methods. At that time, they didn't know the link with control theory, right? This is the interpretation we gave to the topic with Karim Boshar. At that time, they were just using Lyapunov-like techniques, brute force, I will say, take the Fourier transform of the system and then start operating, building Lyapunov functions until you get decay rates of this form, in which you end up, concluding, as they did successfully, that under appropriate Kalman run conditions that at that time, they didn't know it was Kalman, but that can be written as, the condition that the kernel of B has empty intersection with the spectra of all the matrices A depending on C, then the hyperbolic system decays. And actually, you can identify two different components on the decay because the low frequency components decay parabolically. You see the WL component is for low frequency, L for low, that decay like the polynomial T minus M over 2, which is the decay rate of the Gaussian heat kernel, L1, L infinity decay of the Gaussian heat kernel. While the high frequency components, they really behave like wave components with a strong damping for which the decay is exponential. Actually, you expect that the decay rate will be weaker for Xi small. Why? Because you see that when Xi is small, the Fourier variable is very small, the low frequencies, the matrix A has the tendency to vanish. And because the matrix A has the tendency to vanish, the run condition, right, the Kalman interaction between Bi and A becomes very little effective. And this is why the damping that the B is introducing on the system is very weak and then can only guarantee the polynomial decay rate. What we did with Karim Boshar was to reinterpret all this in the context of control theory, using in particular the fact that the Kalman run condition is fulfilled if and only if, right, the adjoint matrix has a zero kernel, right? This led us to introduce the so-called Kalman, we call it the Kalman matrix, right? The Kalman norm, right? Which turns out to be equivalent to the Euclidean norm. And that is simply, combining, superposing the norms of the consecutive iterations B, A, K applied to X from 0 to n-1, as required in the Kalman run condition. And this allows us to more systematically develop new Lyapunov functions by augmenting the classical Euclidean norm through the cascade terms appearing in this Kalman norm, so to guarantee that there was indeed an effective decay that we could measure. In the particular case of the system under consideration, by means of these new methodologies that we introduced with Karim Boshar, we could also further, better analyze the multidimensional systems, multidimensional with respect to a space, in which the classical Kalman rank condition typically fails for some specific values of the dual parameter Xi, and that makes the Shisuta-Kawashima decomposition to fail. But in those cases, we were able to explain, well, even if the Shisuta-Kawashima condition fails, you can still guarantee the decay of the solutions, except for the fact that you will have to decompose the behavior into the three components: the low frequency components, which behave like parabolic, the high frequency components that behave like exponential, but some more singular components that are generated by the Fourier values for which the Kalman rank condition fails, and for which the decay of the corresponding Fourier, say, groups, right? Fourier components will be even a little bit smaller. Okay. Then more recently, when Timothy and Nico were in our team, we thought, well, this is clear for a number of years now. We know how to analyze the decay of hyperbolic partially dissipative systems using the Fourier transform, the interpretation in terms of control theory, and the fact that through these Kalman brackets and iterates, we can build suitable Lyapunov functions to determine rather carefully the decay rate. But comparing with the existing literature, for instance, on the decay of wave-like equations, right, a topic that has also attracted the attention of many, many experts, we observed that there was a gap. Normally, when you deal with the wave equation on a bounded domain, the D'Alembert model or the Maxwell or the Lamé system on a bounded domain, we know that the damping being effective on some subset of the space where waves are propagating is sufficient. And then we said, well, what happens? What happens if we consider the same system, right, with the same matrix A, right, and the same matrix B, right? In this case, I am doing the drawing. The analysis could be done also in multi-D, but I limit the presentation to the 1D case. What happens if the damping B is the same as before, but now is localized only in a set small omega, right, which in this case is just the exterior of a bounded interval minus RR. So you encounter the same linear system as before, but with damping effective only away from minus RR interval, meaning close to minus infinity and close to plus infinity. Meaning, in particular, that while waves are propagating along characteristics as drawn in this, say, red characteristic, there is no damping at all. So the system, along every characteristic, is switching between damping and non-damping, the lack of, because sometimes the characteristic is living on the region where the damping is effective, and some other times, you know, is simply in transition in the space interval minus RR, where there is no damping at all. What happens in that case? Well, of course, our first trial was to try to use the same techniques, so Fourier analysis. But of course, when you do Fourier analysis, it gets complicated, right? Because the Fourier transform of the right-hand side, you know, you have B times U times the characteristic function of U of omega. The Fourier transform of the characteristic function of omega is the Shannon function, which has full support in the whole Fourier space. And this appears under convolution with the Fourier transform of U. So all the components of the system, once you do the Fourier transform, are convoluted, are all interlaced. Therefore, the decay rate is nearly impossible to see. So you see before, frequency by frequency, for every Xi, checking carefully the Kalman rank condition, we could say how much every component was decaying. But now all these components are totally mixed up through this convolution term. Therefore, the task becomes impossible. And this is when we realize that, in fact, instead of using the Fourier analysis here, it will be better to really think in terms of hyperbolic equations to say, listen, to begin with, we need a condition clearly, which says that the eigenvalues of the matrix A cannot be zero. That was not the case before. Before, the only condition I needed was Kalman. Now I need the eigenvalues of A to be non-zero. Why? Because if the eigenvalues of A are non-zero, then I know that they are either negative or positive, but I know that there will be an effective propagation towards the left or towards the right. So there will not be standing waves. There will not be waves that propagate along vertical characteristics without translation in space. Because if they were, these waves will exist, it will mean that if this wave was collocated on this region where there is no damping, this wave will never be damped and therefore will never decay. So we imposed this condition, and with this condition, we were able to show that, in fact, in the present case, under the condition that all the eigenvalues are non-zero, we can prove essentially the same decay rate as we have when the damping is effective everywhere. Why? Well, the reason is what is drawn in this picture. You know, in this picture, there are three regions: damping to the left, damping to the right, just an intermediate region in which waves are not damped. Okay? So what happens then? Well, we have n characteristic lines. All of them are non-trivial. These characteristic lines, of course, will spend some time in this region where damping is not effective. But this will happen only for a limited time window, which is given simply by the length of this interval, 2r, divided by the minimal velocity of propagation. So this means that this will introduce some delay on the decay rate, but up to this delay, the decay rate will be the same. So what we show in that paper is that indeed, under the condition of Kalman that we needed before, plus the condition that eigenvalues are non-zero, you guarantee the same decay rate up to a change on the multiplicative constant, which is related to the delay. Very good. Now, there was another key concept in the title of my talk was hypocoercivity. And I wanted to briefly discuss it to show you how this is linked also to the previous two fundamental topics, right? Control a la Kalman, decay for partially dissipative hyperbolic system, which surprisingly turned out to share the same answer through the Kalman rank condition. So this other topic goes back to Kolmogorov. Kolmogorov was the one to compute. He did this beautiful computation that can be done. I didn't bring it here, using the Fourier transform as well. He was the one who realized that when you take the Kolmogorov equation in the middle, also Fokker-Planck, called Fokker-Planck equation, arising systematically in the kinetic theory of gases, for instance. So you see this equation is surprising, is curious, right? So is f of t, time derivative of f, okay, minus fx, second derivative of x. This is classical heat equation, but then you have a first order term. You have x times the y derivative of f. So the system looks, the equation, this is a scalar equation now. You can make it vectorial, but of course, it's complicated enough for a scalar. This is a system that is in between being parabolic and hyperbolic. And now the surprise was when Kolmogorov made the computation explicitly of the fundamental solution using the Fourier transform, he observed that the fundamental solution has a Gaussian profile. No, people were surprised. How can it be that the solution of this system is a Gaussian when there is no diffusion on the y variable? The diffusion is only on the space x variable. There is no diffusion on y. Yet the solution behaves in a Gaussian wave, right? So why is that? Well, it's due to the fact that, again, in this case, the x and the y variable operators are interacting. And actually, This was one of the fundamental contributions of Hormander, who in his celebrated paper on hypoellipticity, he coined the term hypoellipticity precisely to describe those systems a la Kolmogorov for which, even though solutions, I mean, the problem is not parabolic, solutions exhibit this same infinity regularizing property, right? This is the class of hypoelliptic equations that are not as regularizing as parabolic, but sufficient to guarantee the same infinity characters of solutions. And not only he introduced the concept and identified Kolmogorov as being one of the examples of those systems, but actually he fully characterized those systems, again, through a condition which is very similar to Kalman, in which you iterate the Lie brackets between the two generators of the system, in this case, the second derivative in x and on the other x dy, right, to show that this generates a full, group dissipating all the components of the Euclidean space and therefore guaranteeing hypoellipticity. It was later in the works of Cedric Villani and collaborators where they slightly modified the perspective. They said, well, Hormander introduced hypoellipticity. Hypoellipticity is good to understand the regularizing effects of the linear PDE, but they were interested on the equations of gas dynamics that were nonlinear. So they needed to have energy-like methods, right, to show that due to the interaction of the two terms of the equation, one could gain decay, right? And then they said, well, instead of calling it hypoellipticity, we will call the energy version of hypoellipticity, we will call hypocoercivity. Why? Because we want to show that by augmenting the classical L2 energy, right, using the interacting, the interaction terms between the two generators of the dynamics, we can enrich the energy to a Lyapunov function for which we can show effective decay. Maybe there are several proofs of such phenomena. Probably the simplest proof is the one by Euro that we later adopted in a paper with Alessio Porretta in order to prove the numerical discrete version of hypoellipticity. And as I said, again, the ideas are very similar as in control theory and balance system, because we have to really split the, say, skew symmetric and the dissipative part of the system, analyze the interaction through the Kalman or Lie brackets to gain dissipativity of the missing components, and in this way produce the decay of the full energy of the system, something that in the very particular case of the Kolmogorov equation was discovered by Kolmogorov himself through an explicit computation. So now you see, we have Kalman for control of finite dimensional systems. We have the theory of the balance laws, the asymptotic behavior, where the same condition was encountered. And we find, finally, that in the context of hypoelliptic and hypocoercive PDEs, the same tools appear. The work we are doing now, but in which there is still plenty to be done, and even, I will confess, some doubts that we can really get as far as we will wish. The idea will be what? The idea will be, okay, let's go back to the conservation laws with damping, and let's try to prove the decay without using the Fourier transform. So why would we like to avoid the Fourier transform? For instance, to be able to deal directly with nonlinear systems. This will oblige us to avoid the Fourier transform. What is the difficulty by doing this? Is that now, right, a problem in which we absolutely see how sensitive it is to the different Fourier components. Now we have to be able to build Lyapunov functions globally without discriminating the different Fourier components. This is something we were able to do in 1D, right? But this is still far from being well understood in multi-D because, of course, I mean, in 1D, there is only one Fourier variable, right? And the only thing that matters is the modulus of the Fourier component Xi, while in the multiple space dimensions, there are different Fourier directions, and therefore it's much harder to make a full analysis and description of the dynamics if we are not allowed to discriminate in the Fourier variable. This is really a very challenging topic to which you are all welcome to join. So the conclusions are that indeed, once again, we encounter this fantastic unity of mathematics in this little area in which apparently totally different problems merge to require of the combination of the similar ideas and techniques. There is still a lot to be done, as I mentioned before, to understand the behavior of hyperbolic systems without employing the Fourier variable. And this is actually something that is very hard to do. You are also welcome to have a look to this Cyan review paper, very beautifully written by Haydn on the classical theory developed by Kreis for hyperbolic systems. In that paper, they are analyzing simply the behavior of a linear constant coefficient hyperbolic system with a wall, you know, a boundary condition in which waves are reflected, right? When they reach the boundary, they are reflected. So this very elementary interaction, and you already see in that paper that this is something that in 1D you can handle, because in 1D, you know, there is only one direction of propagation, right? So all the, you know, all these tennis balls are propagating along the X direction, they hit the ball, and then they have to bounce back. The only thing you have to do is to analyze the linear algebra of how the energy incoming in one characteristic line is distributed in the other outgoing characteristic lines. But as is described in that paper, as soon as you go into the multidimensional case, then you have a, you know, you have a wall, right? And then there are different angles of attack of this tennis ball to the wall, and this produces a diversity of possible bouncing phenomena that definitely they depend on the angle of attack, and this is something that is extremely hard to understand without manipulating hyperbolic ideas through Fourier analysis techniques, right? And this paper is a good example of how hard it will be to get rid of Fourier. On the other hand, we need to do it somehow. We need to integrate Fourier in a more flexible manner if we want to get into, you know, more challenging models like those, including non-linearities beyond this, say, threshold in which we were able to employ linearization techniques. Thank you for your attention. Thank you for inviting me for this fantastic event, and thank you for all those that, despite being on Saturday, we're here to listen and to join. Thank you.
Thank you so much, Professor Sosua, for your excellent talk. Now it's time for your question. Do you any question or commentary?
Maybe I have a question for Professor Sosua. Yes, Professor, thank you very much for your very inspiring talk. I would like to ask, for example, in the controllability model that you were describing, how much one can say if one change, let's say, the condition, the topological condition of omega, and one change that omega is an open subset, and one consider one measurable set. Is this of interest in your model? Here, yes.
Yeah, you are here, right? Yeah, so yeah, this is a very good question, actually. I think, right, but we should be careful. We should be careful. I think that in the principle that the decay should be the same up to an increase on the multiplicative constant due to the delay. This principle should remain if instead of having just one interval minus RR, right, where the damping is absent, you have several intervals, right? Then you could think of having infinitely many intervals. Or you could even go beyond and think on Cantor-like structures, or simply, as you said, right, that the support of the damping is a measurable set, right, which is sufficiently thick, right? Now, the question will be, in your opinion, what do you think will be the condition that will be needed on this measurable set so that the damping is effective? What do you think will be a natural conjecture in that case? So you see, in some sense, you have to say the support has to be large enough. Maybe it's measurable, maybe it's made of many pieces, right?
Right.
Like a Cantor set, but it has to be thick enough so to have decay. Of course, you know, the damping will not be effective if the damping is just collocated on one point, right? So that will be non-visible in the L2 setting, you know, sets of zero measure will not suffice.
Right.
But it's not only being of positive measure is not sufficient, because you will have a set, right, like an interval of damping, which is concentrated, and then there is no damping to the left and no damping to the right. In that case, there will not be exponential decay, right? Because then waves departing very much to the right will go to infinity without never crossing the damping region. So you need some condition on the measurable set so that every ray, either going to the left, to the right, independent on where they are starting, spends sufficient time on it. What do you think the condition could be?
Is maybe I am wrong, but this one by Bardos, Le Bon Roche, like the one.
But this is an open condition. I mean, this condition is not well designed for measurable sets. I mean, for open sets, yes, but
okay.
So if you're thinking on measurable set, you basically, I think you will need a condition, something like, my guess is that the condition should be something like, take the measurable set where the damping is effective.
Okay.
Take the intersection with any ball of radius R and guarantee that this set contains a uniform percentage of the set. So that the measure of the measurable set where the damping is effective, restricted to the interval minus RR, is of the order of R. Because otherwise, it could well be that this measurable set is of positive measure, but is not damping strong enough at infinity. So you need to know, for instance, a periodic pattern will be fine, in my opinion, right? So you take a damping on an interval, and then you reproduce it in a periodic manner. I think that will be fine. But you cannot let damping supports, which are very concentrated in the middle and then very scattered at infinity. This is an interesting topic indeed.
Thank you very much.
Thanks to you.
Thank you, Duban. Thank you, Professor. A curiosity, Professor, in is one-dimensional linear hyperbolic system, is possible extend this ideas high dimension?
Yes, so as I said, so here, the problem for conservation laws here is formulated in the multidimensional case, right? In principle, we are dealing with fluid mechanics, gas dynamics. It makes sense in 1D, but of course, most applications are in 2D, 3D, and so on, right? So the problem is formulated in multi-D. The linearization techniques work in also in multi-D. The use of Kalman-like control-inspired techniques can also be developed in multi-D, but as I explained, in multi-D things are much trickier because whether or not the Kalman rank condition is fulfilled depends very much on the directions C in which, you know, we are analyzing the behavior. So the geometric algebraic structure of the set of possible singularities and how they affect the behavior of the linear hyperbolic system is rather complex. So when you move from 1D to multi-D, I will say, it's not only about the support of the damping region, as we were discussing in the previous question by Duvan, but now you have to integrate, right, the very sharp understanding, which requires of tools from algebraic geometry, on the possible singularities Xi and how much the decay rate degenerates on these singularities.
Thank you, Professor. I have a question or commentary. No chat. I have a question or commentary.
Maybe other question, because Professor Suazua, you are an expert, of course, one of the more recognized experts in control theory. This is not a question about your talk, it's more about one philosophical question. What do you think, or what comment you would like to share with the attendees of the conference about, let's say, about directions, research directions in the idea of control theory in partial differential equations?
Yeah, that's a very good question, right? So actually, we didn't talk here about something that is extremely interesting also, which is inverse problem, right? So inverse problems is another neighboring topic. So normally, you know, the way we formulate PDE problems is like in here, right? Of course, we all assume that F is given, the fluxes are given, and the Q is given, right? And then once the PD is given, so we say, let omega be a bounded domain. Let's consider this hyperbolic system where the nonlinearity F is like this, and the damping term Q is like that. Now with this, I show global existence of solutions, decay, and all this. Okay, fine. But in practice, of course, when we face real applications, the nonlinearities are maybe not known, right? We know, well, this is a fluid, yes, but what is the viscosity of this fluid? And we all know that fluids, right? Air, water, and honey are not the same, right? Actually, we can swim on water, but we cannot swim on air because otherwise we'll be able to fly. And it will be complicated also to swim on honey, too much viscosity on it, right? So in practice, then, parameter identification, inverse problems is a fundamental issue. Now, how do we teach to our students, right? We teach piecewise. We say, okay, this is ordinary differential equations. This is partial differential equations. This is mechanics. In mechanics, you learn how the choice of the different models is relevant, what the role of the different constants is, right? Like the Lamé constants in elasticity or the viscosity coefficients. Then we do control. If you give me the system, I can control. And then there is the colleagues in inverse problems that say, well, we help you to identify the relevant parameters, the relevant coefficients, the relevant nonlinearities of the system. Now, in practice, all this has to be merged, has to be done simultaneously, right? So when you are facing a real application, the experts have to know mechanics, to know that they are dealing with fluids, right? And know what are the relevant models for fluid dynamics. But they need also to be sensitive, to be careful about the choice of the parameters because they are facing a specific application. They are building steel, right? For instance, right? And then they have to really tune the parameters properly for their application. And then they have to manipulate the processes and actuate on the processes in an optimal manner so that the steel they get has the level of purity and quality that is required. So in practice, all these merges. And of course, in practice, even though you have all the theoretical know-how, you have to implement all this in the computer, because it's only the computer who will tell you what is the optimal amount of mixing or switching in the mixing pattern and so on that you have to, develop in order to get the product of the quality you want, and of course at the minimal cost, right? In time and investment. So everything has to be done simultaneously in practice. So there is already a lot to be done, Duvan, on merging all these ideas. This is why, for instance, we wrote this paper with Alessio Porretta on the numerical hypocoercivity, right? We said, well, Hormander introduced the concept of hypoliticity to explain why Kolmogorov found this very model and what is the, fundamental explanation of why these systems behave that way. Villani and collaborators developed the corresponding hypocoercive version, meaning that they made the translation from the microlocal analysis of Hormander to building energy functionals and Lyapunov functionals for decay and for energy estimates. We did a translation into the numerical world, right? Why? Because you definitely want that when you make the numerical discretization of these partial differential equations, the key properties that you have observed at the continuous level are preserved at the numerical level. Otherwise, what the numeric says, it will not be relevant, right? If you are not able to guarantee that the long time asymptotics of the numerics is the same as the one of the continuous model. This, in the context of ordinary differential equations, this has a name, right? So these are the symplectic integrators. You have beautiful books by Heider and Warner, Heider father, right? Ernst Heider, one of the pioneers of this field, in which it is well known, right, that yes, you can integrate Hamiltonian systems with many numerical schemes. Many numerical schemes are convergent in the classical sense of numerical analysis. But the convergence in the classical sense in numerical analysis only holds in a finite interval. If you want the convergence to be global in time, if you want to guarantee that the numerically discretized Hamiltonian system has the right asymptotic behavior as t goes to infinity, you need this numerical scheme to be, symplectic. And then you can identify, for instance, the subclass of Runge-Kutta schemes that do preserve such property. This is a very important topic, right? Because in particular, right, when you are solving the solar system, right, you want to make sure that you are able to track trajectories in a sufficiently long time. It's relevant to know whether the moon will collapse with Earth or not, right? I think you all agree, right? So all this is needed at the PDE level. So to make this discrete, there are efforts, right, that has been very successfully developed, for instance, in harmonic analysis, right, to switch from continuous numerical analysis to discrete numerical analysis, making sure that you match the two fields, right? That, for instance, the dispersive estimates you see for dispersive PDEs that you can measure in terms of LP, LQ decay, and so on, are preserved at the numerical level. These are very interesting topics. And nowadays, when you look to even more advanced applications in engineering, right, in particular in the area of machine learning, you discover, for instance, what is called reinforcement learning. Reinforcement learning is a very interesting topic, and my take to it is of course very simplistic, but somehow I will say that what you do in reinforcement learning is basically solve both the inverse problem and the control problem in one shot. Right? As I said, we will tell our students, first you take the book in mechanics. Out of the book of mechanics, you adopt the equations you are considering, either elasticity or fluids. Then solve the inverse problem to identify the coefficients, the nonlinearities of your PDE. Once you have the PDE, analyze the Cauchy problem. Once you have analyzed the Cauchy problem, do the numerics. And then eventually do the control. Then people, engineers in reinforcement learning, they say, well, listen, we don't have the time to do all this. We need to operate in one shot. And how do humans behave? Well, we humans, we learn about the system by controlling. How do we learn about a city? By walking around, exploring. We discover and we integrate in our brain the map, right, of the city map, right, by walking around. How do we learn about, the valley? Well, hiking. How do we operate with a new telephone or any other gadget? I mean, if you offer me a new telephone, I will not read 500 pages of instructions to operate my phone. I will just turn it on and intuitively I will start operating. And by operating, I will learn, there are new devices. Oh, you see, the photo app is very nice because it allows for better, say, a more successful post-processing of the pictures, for instance, right? Or, I have new gadgets to, I don't know, for my calendar or for my health app. How do you learn about this? You learn by operating. So in practice, and this is what reinforcement learning does, it says, listen, you should not wait until you have fully identified your system to start operating on it. You do mathematically as humans do. You start operating on the system, and every time you have the opportunity to see the response of the system, you enrich your understanding of the system. And in this way, the next time when you have to operate the system again, right, you have further information to operate the system better and so on. Then I will invite all to, try to invest in this kind of directions in which we merge all our know-how in one single program, because this is something that has been done successfully by engineers in the context of reinforcement learning, but very often away from the PDE theory. Normally, the models they consider are Markov chains. So there is plenty to be done in the context of PDE to develop, effective reinforcement learning methods for PDE. Thank you for this very interesting question.
Question or commentary? Question or commentary? Well, if there are no more questions, thank you again, Dr. Josua, for your amazing plenary, and see you in other opportunity. Duban, please.
Okay, thank you. Thank you very much, Professor Limaco. Thank you, Professor Suasua, for this, I repeat, very, very amazing talk, very inspiring for Latin American researchers. So, Professor Suasua's talk was the last of our conference. So, I will maybe share with you in this closing ceremony that will start in some minutes, some words about ICMA in Latin America. I would like to share something about our projects, something about our history, and something about our future plans. So maybe I will share my screen. So please, Professor Limaco, could you tell me if you see my screen? ¿Se ve bien la pantalla, Profesor Limaco?
Good. ¿Se ve bien?
Thank you, thank you. Okay, so let me just, as I mentioned, share some words in this closing ceremony. We had with us this week several of the PDE analysts that have changed our perspective on the field. It was my pleasure to be in contact with these recognized researchers and to see that they were happy to support our conference. I know that our Latin American researchers have appreciated this opportunity. So thank you to all the attendees of this conference for your participation. So just let me share now some information about our organization, about the ICMAM Latin America organization. So first of all, I would like to thank to the organizers. I would like to thank to Brian Grajales from Universidad de Campinas, to Professor Julio Delgado from Universidad del Valle in Cali, Colombia, to Professor Juan Limaco from Universidad Federal Fluminense in Brazil. It was my pleasure to work intensively with this very nice team. When we announced our conference, several international societies, like the Belgian Mathematical Society, took attention into our conference and indeed dedicate some space, for example, in his newsletter, informing to mathematicians in Europe about this conference. So it was very nice to have this very nice team. Let me also say thanks to the scientific committee of this conference. This conference was supported by the ISAAC Society, which is the International Society for Analysis, Its Applications and Computation. So our scientific ISAAC board was formed by the ISAAC somehow scientific board. So here you can see the list of all the people that were elected in this activity. Thank you very much to our speakers. It was very nice, really very nice to have them in our conference. So just let me mention how this project born 3 years ago. We start with a local conference in 2020 in Colombia, in Universidad del Valle. And in that time, that we did was to organize one local conference. In that time, the speakers were, as you can see, young mathematicians, postdocs and PhD students, some junior professors. And then we opened in that time, this was a virtual conference, and we opened the participation not only to people from Colombia, but also to people from Latin America. And it was very nice to see that we had the participation of 12 countries. So the past year, in 2022, we continue with this initiative, and then we're thinking about the potential that has this digital initiative. We create this Congress, the International Conference, Multidisciplinary Aspects in Mathematics and Its Applications, 2022 Latin America. We pass somehow from Colombia, from one Colombian and local project to one Latin American project. And then we invite somehow a very nice specialist, like you can see here, Professor Terence Tao, that is very recognized because he was awarded the Fields Medal, Professor Michael Ruchansky, Professor Simon Donaldson. You can see also the participation of Professor Enrique Suazua, that also supports our conference this year, Professor Carlos Koenig, that until the past year he was president of the International Mathematical Union, Professor Dos Santos Ferreira, Professor Tatiana Toro, who from this year will be the vice president of the International Mathematical Union, and Professor Harald Helgoff. Of course, we had also other speakers. It was very nice to have, for example, Christine Lauter from Meta, and many others very nice mathematicians that provide us with very nice talks. So in that time, one of the innovative somehow initiative was to incorporate to our conference one scientific board. So we had with us the support of Emmanuel Carneiro from the Abdul Salam Mathematical Institute in Trieste, Abdul Salam International Center for Theoretical Physics in Trieste, from Professor Alicia Dickenstein, who is a former vice president of the International Mathematical Union, Professor Awe Kaller, who is current president of the ISAAC Society, the International Society for Analysis, Applications, and Computations. We get the support of the Colombian Mathematical Society, the Universidad del Valle, and the Universidad de Pamplona. And you can see, the organizing committee was a mixture between young mathematicians and somehow senior mathematicians that were behind of the organization. So this year we growed as an organization. We create this somehow project, ICMA in Latin America, and somehow our goals essentially are three main goals. One of them to work for the visibility of the research of young mathematicians. Second, to allow to these young mathematicians to be in interaction with recognized mathematicians like we had in this conference. And our main goal is to allow to the women in Latin America to share the mathematical experience with our community, to allow the visibility of women in mathematics in our region. So now this project had exactly two directors, Brian Grajales, who was main organizer of this conference, and me. And as you can see, we have a very nice team, several of them young mathematicians from Latin America. And it was very nice to see how our scientific board growth from the past year to this year. And you can see the past year we have 7 members in our scientific board, and now we have somehow around 40 mathematicians that are involved in this initiative. So the project then grows. The project is growing also, and then we get the support of the Sociedad Matemática Mexicana, the ISAAC Society, the Colombian Mathematical Society, the Autonomous University Metropolitan of Mexico, the Universidad del Valle, the Ghent Analysis and PDE Center, and of FWO, which is the Belgian Research Foundation. So let me share with you our information about our future conferences. We will have in November this very nice conference in satellite conference in data science and machine learning. Again, we will have a talk by Professor Enrique Suazua. We will have the participation of Macarena Esteves, the participation of Ms. Baranjan Senapati, and the participation of Camelia Goga. This will be our main speakers for this conference. It will be in November 17 this year, and you will receive the invitation to attend this conference. The organizing committee this time will change from academia and will include somehow people that is working in companies like Edgardo Barraza Verde Soto from Colombia, and like Alexandra Garcia Medina, who now is working in Alliance, which is, very well known because it's a partner of the insurance partner of the Worldwide Olympic and Paralympic Games. So more information about our future conference. We will have in 2024, March of 2024, the Satellite Conference on Lee Theory. It's my pleasure to announce that this conference will be chaired by Dr. Brian Grajales, who was the organizer also of this conference. He is a young expert in this field, and he will be the main organizer of this conference. So also for the next year, we will have 2 main conferences. Between July and October, we will have the version of the ICMA in Latin America 2024, and then we also will expand our activities to Europe, and it's my pleasure to announce that we will have the ICMA version for Europe in 2024. About this is all that I can share with you about our conferences, our scientific program, but also in ICMA in Latin America, we have some research activities, for instance, to allow the women in mathematics to have visibility with other researchers from Latin America. These 2 young mathematicians, Yuriko Pitones from Universidad Metropolitana in Mexico, and Karina Navarro Gonzalez, that now is in the University of Sao Paulo, but that later will start her postdoc in the Armenian lab of the Ghent Analysis and PDE Center will be behind of the edition of one book with the Trends in Mathematics, which is a book series of Springer. And then we will have, because of the Jet Ford, this book about women in Latin America, women in mathematics from Latin America 2024. We expect to have this book then for the next year. So remember, I mentioned maybe this in the opening ceremony. Also, we have, now we are preparing this Springer volume about the analysis and PDE scientific program that we have the past year in the main conference of 2022. We have then this book in preparation that I am editing with Brian Grajales. And also it's my great pleasure to announce that for this conference, for the Analysis and PDE Conference in Latin America 2023 that we are closing, we will have also one Springer volume with somehow proceedings, receiving contribution of researchers from all Latin America. So this time, the editors will be Karina Navarro Gonzalez, Brian Grajales, and Duan Cardona. So ICMA in Latin America somehow is committed with the visibility of the somehow research of analysis and PDE also, not only from Latin America, but allow visibility of our young generations in other scientific societies like the ISAAC, the International Society for Analysis, Applications, and Computations. And then it's my great pleasure that the ICMA in Latin America, in representation of Colombia, will organize the main conference of the ISAAC Society, which is the ISAAC Congress, that will take place in Barranquilla, Colombia in 2029. So this is very nice to see because, for example, this conference was organized in the past in very nice somehow institutions like the Imperial College London, like the Universidad de Aveiro, like in Ghent University, like the Universidad de Sao Paulo. So this is maybe just to show that the ICM Latin America started like a local congress, but now it's a society, and that in the future has very nice plans. So
Funny enough, he also puts the things on. Oops.
It might then I would like to finish then this this closing ceremony, just saying thanks to our organizers from Colombia and our organizers from Brazil, right? That were behind of this of the organization of this conference. So thanks to our Colombian organizers, thanks to our Brazilian organizers, thanks to the Sociedad Matemática Mexicana, the ISAAC, the Colombian Mathematical Society, the Universidad Autónoma Metropolitana, to Universidad del Valle, to the Ghent Analysis and PDE Center, and to the Belgian Research Foundation for their support. So thank you very much. I don't know if Professor Limaco would like to share some words.
Duan, please. I would like to thank the great speakers for giving us brilliant talk during the week. I would also like to thank you, participants. We contributed to the success of this event. A very special thank you to our sponsor for their support in holding this satellite conference and analysis and partial differential equation in 2023. And many thank you the scientific committee and the organization committee with Professor Duan Cardona, Julio Delgado, and Brian Grajales. Thank you very much for everything, and see you in your next time. Duan, thank you.
Thank you very much. Okay. Karina Navarro Gonzalez is here. Okay.
Yes, I am here. Hello, everybody.
Okay. It's my great pleasure to introduce to all of you to Karina Navarro Gonzalez, who was also co-founder of this project. So as you can see, there are many young researchers behind of ICMA in Latin America. So thank you, Karina, for being here.
Thank you. Thank you too.
Okay. Okay, thank you very much. So I think we can close our conference. Thank you to all the participants. Thank you, Professor Suazua, for being here. Thank you, Professor Limaco. Thank you, Professor Jennifer Agnelli. And thank you to all the participants. So see you next time.
Gracias, Duan. Gracias.
Thank you very much.
Gracias.
Bye.
Pronto. Hasta pronto.
Arrivederci.
Gracias.
Ciao.
Bye bye, Sebastián.
Bye, Duan. Thank you.
Bye, Duan.
Bye.
Thank you very much, Duban. Bye.
Muchas gracias a todos.
Gracias, saludos. Hasta luego.
Hasta luego.